This video is about using integrals to find area. We can recall that by definition, an integral, what we call the definite integral from a to b, is actually an infinite sum of infinitely skinny little rectangles. The function f of x gives you the height of the rectangles, and delta x, which operates in a range from x equals a to x equals b, that's divided into n rectangles, delta x is getting infinitely small. That means the number of rectangles, n, is getting infinitely large. When the rectangles get infinitely small, and the number of them gets infinitely large, this infinite sum is really, particularly if the function is above the x-axis, is really a good, almost perfect estimate of the area between that curve and the x-axis. And that's where we got the idea that our integral was an area. So this is our definition, and while it helps us understand what an integral is, it doesn't help us find an integral. We have been collecting evidence that these sums, which we approximate with real sums of lots of rectangles, we're not really calculating sums of infinite numbers of rectangles, but we've been finding these sums and finding out that they're surprisingly similar to the difference between the antiderivative. And that's why we say, here's a conjecture that we haven't proven, but we're collecting evidence for. The definite integral from a to b of lowercase f of x dx is the difference between the antiderivative of lowercase f, we're calling it capital F, f of b minus f of a, the upper limit of integration minus the lower limit. And we are very clear that the relationship between capital F and lowercase f is that the derivative of capital F is lowercase f, and capital F is the antiderivative of lowercase f. We have not proved this yet. That proof is a proof of the fundamental theorem of calculus. But we have been watching this. We have been calculating estimates of this infinite sum, and we have been calculating this difference of antiderivatives, and we've been finding that they are very close, in fact. So we're going to look at some more examples now and continue our study of how to use integrals to find area. So our first example is new in that we're using a function, y equals x cubed minus 4x squared, that has an area below the x-axis. This area is, going to be positive if you really think of it as area, but all the y values are negative. You can see that. I showed that in all the points. So if you just sum up what we were doing before, the delta x's times the heights, you're going to get a negative number. So let's go ahead and let's do this. We're going to take this function, divide it into 8 right-hand side rectangles between x equals 0 and x equals 4. We're going to add up what would be the area of those rectangles without thinking about positive or negative heights, just doing the sum of the sequence. The base of each rectangle is a half. Remember, we take the range 4 minus 0, we divide by the number of rectangles, 8, and we get delta x is 4 over 8, or 1/2. So the base of each rectangle is a half, the height of each rectangle is on the function, x is the variable, we're taking the right side of every rectangle to get the height of the rectangle, and so the first one is x equals 0.5, the last one is x equals 4, and the delta x is 0.5. And when we do this, we get negative 21. We get a negative number, and it's not because there is such a thing as negative area. It's because we're not really calculating area. We're calculating a sum that could be area if we take its absolute value. So we can find out that the magnitude of this space is 21 and call that the area. Okay, so let's just see what would happen if we used 100 rectangles. With 100 rectangles, our delta x changes. 0 to 4 is the range, so 4 minus 0 over 100 is 0.04. And so 0.04 is the base of every rectangle. We're using the exact same function, and only the first x value, 0.04, and the delta x change. The last x value is still 4. And notice we get very little change with 100 rectangles in this case. We get negative 21.3312. That's very close to the negative 21 we got before. So here's a case where going from 8 to 100 rectangles didn't improve our estimate all that much. Notice though, of course, it's still negative. So let's try the integral method. We're taking the integral from 0 to 4 of our function, x cubed minus 4x squared. And the way we do that is find the antiderivative. So the antiderivative of x cubed is x to the 4th divided by 4. And the antiderivative of negative 4x squared is, is negative 4x cubed divided by 3. Talking a lot in these videos requires some liquid. So we take the antiderivative at x equals 4 minus the antiderivative at x equals 0. We did not forget the plus c's. But when we subtract, c minus c is 0. So as we get used to doing integrals, particularly when we're doing definite integrals, we're going to forget to write these plus c's because they always drop out. Okay, so if we plug in x equals 4, we get 4 to the 4th divided by 4, minus 4 times 4 cubed divided by 3, and then this is 0, and 0 to the 4th and 0 cubed is 0, and the c minus c is 0. So the only terms we get that have any value are the first two here. And we get negative 64 over 3, or negative 21.333. Again, so very close. Clearly it looks like our sum, our infinite sum of skinny rectangles, is the difference between the antiderivatives, because even at 100 rectangles, look how close. But clearly also our sum doesn't know anything about positive or negative, it's just adding up the values. So we have to be careful if we want to use this for area. We have to separate the positive and negative spaces so we can get all their sizes and add them together properly. So let's look at another example. Here's a well-known function, the function y equals sine x. Sine x goes up and down and up and down, and it has positive spaces with the x-axis and negative spaces with the x-axis. The green here is positive, the pink here is negative. You can see the positive y values, and you can see the negative y values. So the first thing I did here was to divide the area from 0 to 2 pi into 8 rectangles. So 2 pi minus 0 divided by 8, 2 pi over 8 is pi over 4. So pi over 4 is the base of each one of these rectangles, and sine of x is the height. X is the variable. We're doing right-hand side rectangles, so pi over 4 is the first x value we plug in to get height, and 2 pi is the last. And delta x is pi over 4, and when we do this, we get 0. And that's something you might have thought when you saw these areas. You might have thought the positive and the negative areas are probably symmetric. All right, well, let's try doing this with some more rectangles. You should notice here that for some reason this says triangles, but it should say rectangles. So 100 rectangles. We do the same thing to find delta x. We take the range, 2 pi minus 0 divided by 100, which is pi over 50. And remember, we're doing our Riemann sum using the sum of the sequence on a TI-83 calculator, and there are instructions posted on your Google Classroom in order to find that value, in order to use that calculator to find these values. So the sum of the sequence of the rectangles, pi over 50 is the base, sine of x is the height, x is the variable. These are right-sided rectangles, so pi over 50 will be the first x value plugged in to get the height, and 2 pi will be the last. Pi over 50 is delta x, and when you do this, you can do it a couple of times, you don't get 0 anymore. You get a very, very tiny negative number, almost 0. It's worth considering this for a minute, though, because you have to remember that depending on how many rectangles you create, you can introduce a little bit of error, and this one introduced a teeny tiny bit more of the negative space because of the way the rectangle areas were measured. So we're getting 0 over and over. Let's try the integral method. So here we're going to do the integral from 0 to 2 pi of sine of x dx. The antiderivative of sine of x is negative cosine of x. And we evaluate it at 2 pi, and we evaluate it at 0, and we subtract. And when we do that, unsurprisingly, we get 0, because this summed up the positive and the negative spaces. But if we separate it into two integrals, just the positive from 0 to pi, and just the negative from pi to 2 pi, we get the antiderivative and we plug it in, take the difference, we get positive 2 for the positive area and negative 2 for the negative area. Instead of adding these together and getting 0, we add together their absolute values. So we get the total area is 4. So if we think about this, in order to properly use integrals to find area, we have to reliably figure out what areas will be positive, what areas will be negative. We'll have to use the graph and other information we have so that we can separate these integrals. Of course, we are still working on a very big assumption. We are assuming the fundamental theorem of calculus. Is it true? Is it always true? How do we know? We have not proved it yet. Stay tuned.